Hello, dear learners. My name is Professor Janku. Welcome to our session. Before we continue, your advice to comment this video, like and share this video, and feel free to subscribe to this YouTube channel. And if you're interested in a one-on-one online session, you can email me at the address ftpriest@yahoo.ca. What are we going to learn throughout the session? I will guide you through finding general solutions to trigonometric expressions or equations precisely. We are going to explore the techniques involved in solving equations containing sine, cosine, and tangent function. Why is this topic very important? Because this topic, precisely trigonometric equations, can be used to model real-world phenomena like sound waves, light waves, and many more. And it's also important in the GPS and navigation system. Take note that GPS systems rely on trigonometric principles. For instance, they calculate positions using angular measurement. So this is just to name a few. There are a lot of applications of trigonometric equations. So pay attention to what we follow so that you can be able to apply this whenever you encounter one of these aspects of phenomena in real life whereby you have to solve trigonometric equations. So what are you going to learn? You're going to learn how to master the techniques for finding solutions to equations involving sine functions. You're going to learn the systematic approach to solve equations involving cosine functions. You're also going to discover techniques for determining all solutions to tangent equations. Here are a few basics you have to know. When you're given a trigonometric equation, you have to first identify all the functions involved in the equation. You have to see how you can find the principal solutions. You can also apply periodicity to find all possible solutions, and then you have to express the general solution. Here are a key step-by-step approach towards how to solve a trigonometric equation. Firstly, you are advised to use algebraic methods and trigonometric identities to solve or simplify the equation. Secondly, you have to find the reference angle using the positive value. Thirdly, you have to use the cast diagram to find where the function is positive or negative. Fourthly, you have to find the angles that lie within a specific interval by either adding or subtracting multiples of the appropriate period. Fifth step consists of obtaining the general solution. How do you do that? You have to get the angles in the interval 0 to 360 degrees that satisfy the equation, and you have to add multiples of the period to each answer. And don't forget, last step, to verify your answer using a calculator. These are key basic formulas you have to remember. These are the basic trigonometric equations that you might encounter. The first trigonometric equation under consideration is sine theta equals to x. We want to find the value of theta for which this equation holds. Therefore, the solution would be theta equals to inverse sine of x plus n times 360 degrees, or theta equals to 180 degrees minus inverse sine of x plus n times 360 degrees, whereby n is an element of an integer. Next, you have to consider cosine of x, theta equals to x. Therefore, the solution will be theta equals to inverse cosine of x plus n times 360 degrees, or the next solution will be 360 degrees minus inverse cosine of x plus n times 360 degrees, whereby n is an element of integer. The third basic trigonometric equation under consideration is the equation tan theta equals to x. The solution would be theta equals to inverse tan of x plus n times 180 degrees, whereby n is an element of integer. Let's go through these simple examples so that you can see how to apply the key formulas that was mentioned in the previous slide. The first example is sine theta equals to 0.5. In fact, we are looking for all values of theta for which sine of that angle equals to 0.5. As we did mention here in the previous slide, the solution would be theta equals to inverse sine of 0.5. If you use your calculator, you are going to obtain 30 degrees. And according to the periodicity of the sine function, we have to add 360 multiples of 360 degrees to this solution and elements of integers. Okay. And remember the second solution here. Let's call this theta 1 and let's call this theta 2. The second solution would be, as we did mention in our previous slide, 180, simply because the sine function is positive according to the cast diagram, is positive in the second quadrant. And remember how to write angles in the second quadrant. We have 180 minus 30 degrees. 180 degrees minus 30 degrees. Don't forget to add a multiple of 360 degrees simply because we have the periodic function sine, which is periodic over 360 degrees. So we're going to have this as 150 degrees plus n times 360 degrees, whereby n is an element of integer. So if you check your answer, you have to put into your calculator sine of 30 degrees. You're going to obtain 0.5. Likewise, for sine of 150 degrees, you will also get 0.5. Let's check the second example with cosine of theta equals to minus 0.5. You need to find what we call the reference angle. The reference angle is given by arc cosine or inverse cosine of 0.5, the positive value. We will get 60 degrees. Now, according to the cast diagram, we have cosine positive cosine negative. Don't forget, because of this negative sign you have here, we look for, according to the cast diagram, we have our cosine negative in the second and third quadrant. Second and third quadrant. Okay. So what do we do now? We have to use our knowledge of how angles in each of those quadrants look like. So we're going to check for our first solution in the second quadrant. So we're going to have 180 minus the reference angle. 180 degrees minus the reference angle. Don't forget your multiples of 360, because even the cosine function is periodic, has a period of 360 degrees. So this gives us what? 120 degrees plus n times 360 degrees, whereby n is an element of integers. The next solution will be the one in the third quadrant, which is 180 minus plus 60 degrees plus our n times 360 degrees. So we're going to have, our solution will be 240 degrees plus n times 360 degrees with n element of integer. So we have our two solutions here. Don't forget to check your answer. What you do is that you check, you take your calculator, you punch, you use cosine of 120, you're going to get 1 minus 0.5. You can also check cosine of 240 degrees, you're also going to get 0.5. For the third equation, we will simply have our principal value, which is the only value. The solution will be arctan or inverse tan of 1 plus n times 180. Don't forget to use 180 with regards to the tan function, because the tan function has a period of 180, not 360. So 180 degrees, whereby n is an element of integer. So we are going to have now 45 degrees plus n times 180 degrees, whereby n is an element of integer. These are the worked examples that we've considered so far. So I hope you've seen how to use the key formulas to remember to solve basic trigonometric equations. So let's look at a much more challenging one, which is sine of 2x plus cosine of x. The goal here would be, because here we'll have a double angle, we have to use our well-known trigonometric identity that we've studied so far for double angle to reduce it to a single angle. So we're going to have it as, remember, recall what we did study in our previous sessions. Sine of 2x is equals to 2 sine x cos x. Therefore, we're going to have that equation will now become 2 sine x cos x plus cos x equals to 0. Therefore, we can factorize cos x here to obtain 2 sine x plus 1, okay, equals to 0. So this implies cosine of x equals to 0, or 2 sine x plus 1 equals to 0. We're going to have x will be equal to our act cosine of, or inverse cosine of 0, which is 90 degrees, okay? So our first solution here is 90 degrees. We're going to have 90 degrees here. Plus, remember, our first solution, let's call it our first solution, plus n times 360 degrees. Our second solution will be, remember, according to the CAST diagram, we're going to have the cosine function positive in the fourth quadrant. So we're going to have 360 minus our reference angle that we obtain here, minus 90 degrees, plus n times 360 degrees. So we're going to have 270 degrees plus n times 360 degrees. Remember to always mention that n is an element of an integer. So we're going to have two general solutions for the first part of our solution. The next part will consist of solving this using algebraic techniques. So we're going to have 2 sine x equals to minus 1. Therefore, sine x will be equals to minus a half. We find what we call the reference angle to this is equals to arc sine or inverse sine of a half. An inverse sine of a half is given by 30 degrees, okay? 30 degrees. So according to the CAST diagram, remember the CAST diagram, which is this. According to the CAST diagram, sine is negative in the third and the fourth quadrant. So our first solution would consist of writing angles in the third quadrant. So we're going to have 180 degrees plus 30 degrees plus n times 360 degrees. So we're going to have 210 degrees plus n times 360 degrees. That is the other solution. So the next solution here, with regards to this expression, we're going to have 360 degrees minus 30 degrees. Remember to always mention that this should be an element of integers. So plus n times 360 degrees. So we're going to have our answer here would be 360 degrees minus 30, which is 330 degrees, plus n times 360 degrees, whereby n is an element of integer. So we have four solutions: this solution, this solution, this solution, and this. These are our four solutions. That is a typical example of how to use trigonometric identities to be able to solve trigonometric equation. So what have we grasped throughout the session? We've been able to recognize the patterns precisely to identify a function and its period to determine a general solution of a given trigonometric equation. We're able to use the principal solution and then extend to general solution. And remember to always verify your answer by putting the answer into the general or into the original equation to get the final answer. So thank you for looking at this video. I hope you are now well equipped to solve trigonometric equations. Thank you for following. See you in the next video. Bye.